like 20. We were all like, oh, maybe we'll cancel our class. And then it turned out.
Yes.
I seem to understand this stuff.
I think yeah, this graphic stuff is fine.
Yeah, I think so.
I just did the first chapter. Yeah, some of the stuff in
Thank you.
Oh, they're not open to these guys. Where's John Water Race?
it's too slow. Yeah, well, if you actually do it, it'll help out for your test.
Okay. They had the one that was Friday.
Well, for last Friday? Yeah, that one is about, yeah, there's one for this week, but it's due Saturday, but it's all the same on the test.
It's like this.
Yeah. Well, I guess something from this and something from last week. Because on Thursday we're doing 5.1, which is a whole test.
It's gonna be cool. Yeah, I was walking around this way going.
Okay. 4 o'clock now. Great. Okay. So, before I get started, I remember to actually hand these out this time. I forgot to do the 2.7 handout last time, so I've got it now. If anyone didn't get it, that's why. I totally forgot to hand it out. I also have a couple things about the test that's coming up. I have a page here which is talking about sort of what to expect. It describes sort of the type of questions and how many questions is going to be on the test. And I also have a practice test. Again, one thing to mention about the practice test is designed as a way for you to see how many questions and the type of questions, what sort of questions you could expect. There's a lot of subjects which I covered which are not on the practice test. The practice test is the same length as the actual test, which means there isn't enough space for me to do a question on everything. So definitely, the practice test is most useful as a way of checking your studying rather as a way of studying. So the idea is study from the practice problems I've given you from the book. Once you feel like you're doing well with those, then try the practice test. If you can do well in the practice test, you probably will be able to do well in the actual test. But make sure you study the types of questions which aren't on the practice test. Because there will be questions on the actual test which are not similar to questions on the practice test and vice versa. The number of questions and the type of questions are going to be the same as the ones on the practice test. but the actual specifics of the questions will be different.
If we have
Yes.
questions from the practice test, if we do it and we have questions from it, are we able to do that on Thursday?
Well, what I'm gonna do, and I did because I just typed up the practice test before class.
Yeah.
On Thursday, I'm gonna, well, sometime between now and Thursday's class, probably Thursday morning, I'm gonna type up solutions to the practice test,
Okay.
and I'm gonna hand those out in Thursday's class. So, yeah, so you will have solutions to it, and that's certainly if there's any specific questions, yes, there will be a chance to go over those in Thursday's class. I'll make sure there's time to do that. Yeah. Oh, thank you. Yeah, if there's any extras, just going back on that. Yes. Okay. Any other questions about the test before I get started?
So Friday.
Friday's test, exactly. And yeah. Okay. Okay. So the agenda for today, again, the first thing I'm going to be doing is a couple muddiest points from last class. Then I'm going to be finishing off section 2.7, which is the last thing in chapter 2. And then for the rest of the class, I'm going to do a review, about 25 minutes, half an hour of review. Part of the review will be sort of me giving you a quick summary of everything we've seen, and part of it will be, once I've done that, a chance for folks to ask any other questions that folks have questions about, or to go over specific topics that people are having difficulty with. The other thing to mention about the review is if there's specific things that you can think of that you want to go over next class, feel free to write those in your muddiest point cards. And I'll be able to go over things in your next class as well. And then again, I'll have a group problem at the end. This should be a singular group problem, not group problems. One from 2.7. Okay. So the muddiest points from last class, there were a couple of them that came up. The first one, someone wrote on their card a question about they had difficulty understanding my writing on the board. I didn't understand from what this person wrote on the card what the specific thing was that they had difficulty understanding on the board. So if you do have specific questions like that, feel free to come and ask me and show me your notes, and I can see sort of how to fill in what's the gaps in your notes and stuff like that. Or better would be is if you have a difficulty understanding what I've written on the board, please put up your hand and let me know this. Because if you're having difficulty reading it, there's probably other people in the class who are also having difficulty reading it. I would really like to make it better. So yeah, if there's any difficulty with my handwriting, please let me know before the muddiest point cards at the end of class. Because at that point it's a little bit difficult for me to fix it. So that's the first thing I wanted to mention. Is that, yeah, I can't, by the time the muddiest point cards come around, it's a little bit out of context and I have a hard time understanding what specifically the question is about. So, yeah, if there's questions about my handwriting, please let me know when it's happening. The second one, someone was asking about one of the questions that was on last week's webassign. Obviously, I couldn't have given you the answer before now, and hopefully, is there anyone in the classroom who has not completed last week's web assignment and has a good reason to get an extension on it? Because once I've shown you this, I can't give you an extension on it anymore. So I just want to make sure there's no one here who's going to ask. Okay, anyways, yeah. So I'm going to go over this question from last week's web assign. Again, it was a fairly difficult one. It was one with office space. And the picture looks something like this. Right, there's an office. I think they called this one Y. And this one X. No, other way around. Now that sorry. Yeah, this was X and this was Y, I believe. And we were told a couple things. The first was that the area is 400 square feet. And that the walls cost $200 per foot. Oh, and there's a couple other pieces of information. Each of these doorways is 3 feet wide. So, part A asks to find a formula for Y in terms of X. Well, the key thing is if the area is 400 square feet, this whole office space is a rectangle, right? So the area is the length times the width, which is X times Y. So if you want to find a formula for y in terms of x, you divide it by x. Take 400 over x. And part B asks to find a formula for the cost of the walls in terms of x. Is that legible? I'm realizing my writing is not as good as it could sometimes be. I'm going to rewrite the walls and the terms. So the key thing here is that each wall in this place is a different length, right? This wall, the length of this wall is x minus 3. The reason is because this distance is x, and there's 3 feet missing where the door is. So if you want to measure how, yes?
I thought the question said exclude, like, don't include the spacing of the door.
Exactly. Don't include this in the length of the walls.
Oh, I thought it was.
Yeah.
It was
It
worded
means
funny.
when it says exclude the space for the doors, it means you don't have to pay money to build a wall where the door is. So when you're measuring how much wall there is, in order to pay money for it, I believe, at least that's how I interpreted it. I believe
Yeah, I
that
thought
gave
it was.
the correct answer. I'm pretty sure that gave the correct.
Yeah, it did.
Yeah, it did. It
Yeah.
did. Yeah, I'm thinking about it. I'm thinking about the answers. And I'm like, yeah, I know. Yeah. So the key thing is when it's saying excluding the doors, it means the doors don't. You don't have to pay for the doors,
Yeah.
right? Which means that this distance and this distance is the distance you have to pay for, and these two distances together is x minus 3. Same for this one. That wall is going to be x minus 3. This one's going to be x. The bottom one's going to be y. And the top one's going to be y. So the total length is going to be x minus 3 plus x minus 3 plus x plus y plus y. And if we collect like terms there, we get 3x, because of x, 2y, because y and y, and then a minus 6, we got minus 3 plus 3. So that's the length of the walls. Now if you want to measure the total cost, we're going to have to multiply that by the $200, because it costs $200 per foot. So it's going to be 200 times 3x plus 2y minus 6. Oh, sorry, I just realized I erased something which I'm going to still need. This piece of information. Okay, I'm going to get rid of this marker and switch to the other one. That y is 400 over x, that's going to be important. And that's going to come up again. So, the cost here, 200 times 3x is 600x. 200 times 2y is 400y. 200 times negative 6 is minus 1200. And then you've got to fill in this information, right? This is the formula for y in terms of x. I'm going to put that in there. So we get 600x plus 400 times 400 over x minus 1200. And that's the formula for the cost of the walls in terms of the width of the room. And then what you're going to see in calculus of questions like this is find the x that makes this cost as slow as possible. Find the x that minimizes the cost of the walls. If this is a quadratic function, we could already do that. Right? Quadratic things we can find where their minimum or maximum is using the vertex formula, right? The minimum value of a parabola is always at the vertex. The maximum value of an upside down parabola is always at the vertex. This one's not a quadratic function, so in order to find which the number x which minimizes this cost, you will need calculus. So this is the sort of thing that you will see in calculus. You'll see questions like this, and then it'll be find the x that makes this cost as low as possible. Any questions about what I did here? confusion, difficulty with understanding this. Again, I just wanted to go over this one because, again, there's a lot of people who have difficulty with word problems. And, yeah, the book doesn't... I haven't yet to discover a textbook which does a really good job of explaining how to do word problems. Like, and I try to do my best in class, but I can only do so many examples in class, so I want to make sure I get a chance to do more. Any other questions before we move on?
Do you want us to leave it like that? Or on the website you had to...
They wouldn't accept this. They'd only accept it if you did this.
Yeah.
This is why I don't like WebAssign.
Well, I'm not sure that's just how I entered.
Yeah. Usually, I mean, in some situations they'll accept anything as long as it's what's called algebraically equivalent. As long as it can be simplified to the same thing. Yeah, this is probably what WebAssign wants, is to multiply the 400 by 400 to get 660,000. Yeah. And that's... Now, in some questions, WebAssign will accept either answer. In some, it'll only accept the simplified one. And to be honest, I can't tell which is which until someone types in this one and gets it wrong. So, because, I mean, at some point, once I've taught this course using this textbook enough, I will know, but yes, Kat.
One thing I tend to do if I'm really not sure how it's going to want it, I'll try to do a practice question if they have it, and then you'll see what they come up with.
Yeah, that is actually, yeah, thank you for that suggestion, because that's something I forget about, but the practice questions are there, because I don't see them when I'm creating the assignment, but yeah. Thank you for that suggestion. Yeah.
I was wondering if on a test though,
Oh, on a test, either would be correct. Yeah. If I specifically want you to simplify, I'll put the word simplify in the question. And usually I'll only ask you to simplify if it's a specific algebra simplification question. I won't usually ask, find an equation for it, and then simplify it. Yes? Yeah. 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 Exactly. WebAssign comes with all these helpful buttons like the watch it and the view an example and that sort of stuff. So, yes. That's one of the reasons I like WebAssign. Yeah. And I think it gives better examples than the textbook does a lot of the time. I don't like this particular textbook. Yeah. Okay. Any other questions before I move on to finish section 2.7? Okay. So we're finishing off section 2.7. What I covered last class was 2.7.1, when I talked about adding functions together, subtracting, multiplying, and dividing them. What I'm going to be talking in 2.7.2 and 2.7.3 is what's called a composition of functions. A composition of functions is another way we can take two functions and put them together. However, it's a little bit more complicated than just adding them, subtracting them, multiplying them, and dividing them. The symbol for a composition is this circle like this. Sometimes people think it's an O, and this says fog. It's not quite an O. Computers will always write it as slightly, like an open bullet. If you write an O, I won't, yeah, handwriting, you can't really tell the difference between that thing and an O. On computers, you can. Yeah, it's called composition of functions. How many people have seen this before, F composed with G? How many people have not seen it before? Okay, there are a couple. You have probably, even if you haven't seen it before, you have probably done it before. Because all that this operation means is that first we do this function, and then we do this function. If you've ever been in a situation where you've done something like calculate, oh, hey, here's a great example. Calculate the length, and then calculate the cost from the length. We're actually doing composition of functions here, even though we don't know it. This is one function. What we're doing when we're multiplying the whole thing by 200 is we're composing that thing with this function. The cost is 200 times the area. So when we do one thing and then do another thing, we're doing composition of functions. So the procedure of doing one function after the other is called composition of functions. The way we oftentimes write this is f of g of x. It means first we do g of x, then whatever thing we get out of g of x, we put in to f of x. So first figure out what g of x is, then whatever we get, we plug into f of x. Now one thing that's weird about this notation is we always do the second function first. We do the one inside the brackets first, and the one inside the brackets is the second one that's written. And that's just because we write things from left to right, but the brackets are on the right-hand side. So, yeah. So it's sort of, you do the g of x, and then you do the f. The way, again, oftentimes we'll use this circle notation rather than writing it with two sets of brackets. So I write this, f circle g of x, that means I'm taking f of g of x. One thing to mention, this x is not multiplication. I'm not doing f circle g and then multiplying it by x. I'm taking the x and plugging it into f circle g. So I'm doing this. If it was like f circle g of 2, it would be f of g of 2. If it was f circle g of y, it would be f of g of y. This x is just to tell you what the variable is. So again, I had students on last semester in Math 140 ask them to do this, and they would figure out the formula for f circle g, and then multiply the whole formula by x. This is not an additional multiplication by x, that's just part of the formula for f circle g that tells you that the variable is x. Any questions about this before I move on to examples of this? Okay, so the first example of this, I'm going to do it with a table of values. Now this is in the textbook, I'm going to copy it out onto the board. On page 173. I just want to mention this one because sometimes people think of functions only as formulas. But the idea is a formula is only one way of thinking about a function, and there's lots of functions out there that don't have formulas. And so sometimes we have to work with functions as tables of values. So the first function looks like this. When t is 0, capital T is 2. When t is 1, capital T is 3. When t is 2, capital T is 1. When t is 3, capital T is 0, and when t is 4, capital T is 5. The second one, when x is 0, 1, 2, 3, and 4 again, 1, 0, 3, 2, 5. So these are tables of values for these functions. This says that when the input to this function is 1, the output is 3. So now I want to use those tables of values to find s circle t of 1. What this means is I'm doing s of t of 1. So the first thing to do is to do t of 1. This means 1 is my input, and I'm going to be using the function t. So I look at the table for the function t. Find the input 1, the output is 3. So that means that t of 1 is 3. Now I'm taking s of 3, which means I look at the table of values for s, I find the input 3, and the output is 2. So the two things I'm using to do this, I'm using t of 1 and s of 3, sorry. Just sort of showing what I'm using to do that one. Where did my red marker go? There it is, I'll grab it. The next one is this. I want to do s of 1. Sorry. It's written as s circle s of 1. which means s of 1. So the first thing is I look up what s of 1 is in the table. So that means my input is 1, using the function s, so my output is 0. So I'm taking s of 0. To figure out what s of 0 is, I look up my table for s, find the input 0, my output is 1. So again, here I'm doing one function after the other. Here, first I'm looking it up in t, then I'm looking it up in s. Here I'm looking it up in s, and then I'm looking up it again in s. But the first time the input's 1, the second time the input's 0. Any questions about how I did this? Yes?
Are you still recording all your videos?
Oh yeah! I have not posted, no, I have posted them to YouTube, but I forgot to actually put the links on the course webpage for over a week now. So tomorrow I'm going to try to post all the links that are there, and I'll try to upload as many videos as I can tonight. Again, they're big videos, so it takes a long time for me to upload, so hopefully I can get them all done overnight tonight. If not, then I'll be doing the rest overnight tomorrow night, and then by Thursday they should all be up there. But yeah, thank you for reminding me, because I did realize today that I haven't posted the links in a while, which means the videos are there, but you can't find them. And I think I've set them as unsearchable, because I don't want people... I might get in trouble with the university if people from the other universities start using them. That's the key thing, because it's like only supposed to be people who are in this course who are supposed to be able to see it. And I don't want to make it password protected, so that's why I just have it unsearchable. Yeah. Yes?
What if I provide the link to somebody who's talking a different block or different class?
Oh, different class in this university is totally not a problem. That's definitely not a problem. Different block in the yeah. No, I mean I share stuff with. I'm not currently sharing stuff with. I don't remember the name of the guy who's teaching. Why am I blanking out? Stan, who's teaching the other section, but I am using a bunch of materials that have been shared with me by the person who taught it last year. So yes, sharing with other people in the same university is perfect. Be fine. I'm just not sure. I'm probably people in other universities again. There's weird competition things going on there that might be an issue. Okay. So for example 6, here we've got functions that are given to us by formulas rather than the table of values. And here I want to find a formula for f circle g, a formula for g circle f of g of -2, and g of f of 3. So this is example 6. So f of x here is x cubed plus 2x squared. G of x is 3x. So if I do f circle g of x, that means I'm doing f of g of x. G of x is 3x, so I'm doing f of 3x, which means I'm looking at my formula for f of x, and every time I see an x, I'm replacing it with 3x. So I'm going to get 3x cubed plus 2 times 3x squared. Now, at this point, if you're doing this on the test, I'm totally okay if you stop here. The book always, the entries shown on the back of the book are always simplified versions of these, and we can simplify this fairly easily. 3x cubed, 3 cubed gives you 27, x cubed gives me x cubed, 3x squared, 3 squared gives you 9, multiplied by 2 gives you 18, x squared gives you x squared. So the answer in the back of the book to this question will look like 27x cubed plus 18x squared. But again, if you leave your answer like this is fine for the purposes of the test. What I'm testing is really your ability to go from here to here. The simplification will be asked in other questions on the test. So the next thing I want us to do is g of f of x. So that means we're doing g of f of x. So f of x here is x cubed plus 2x squared. And if I'm doing g of this thing, it means I'm taking this whole thing and plugging it in where the x is in g of x. So I get 3 times x cubed plus 2x squared, which is 3x cubed plus 6x squared. Okay. Next, I'm doing f of g of negative 2. G of negative 2, g of x is 3x, so g of negative 2 is 3 times negative 2. 3 times negative 2 is negative 6. So what I'm doing here is I'm doing f of negative 6, which means I'm plugging negative 6 into that formula. I'll get negative 6 cubed plus 2 times negative 6 squared. Negative 6 cubed is negative 216, I believe. Negative 6 squared is 36 times 2 is 72. That gives negative 144. And the last one, oh, I should have left that part up. If I'm doing g of f of 3, first I do f of 3, which is going to be 3 cubed plus 2 times 3 squared. 3 cubed is 27, 3 squared is 9, 9 times 2 is 18. 27 plus 18 gives you 45. So if I'm doing g of 45, that means I'm doing 3 times 45, because g of x is 3 times x. 3 times 45 is 135. So any questions about how these guys work, finding compositions of functions? No. Okay. Do I have really? Okay, good. It's just I hope I don't have more examples than that though. This last one. I just wanted to show an example of this because sometimes this confuses people when we have a composition of a function with itself. So f of x. So this is example 7. Here we have f of x equals 3x squared, and I'm trying to find f of x. Well, this means I'm doing f of x. My f of x here is 3x squared, so I'm doing f of 3x squared, which means I'm taking 3x squared and plugging it into 3x squared, which means I'm going to get 3 times 3x squared. And again, if you're doing this on a test, I'm totally fine if you leave it like this. If you can simplify it though, that'll be 3 times 9x to the 4th, because 3x squared is 3 squared is 9, x squared is x to the 4th, and 3 times 9 is 27. So a simplified version would be 27x to the 4th. But again, the simplification part is not something I'm going to worry about in these sorts of questions for the test. That's example 7 between those two lines. Any questions?
Sorry, where can we stop? The 3.
Here.
Okay.
Yeah. Yeah, as long as there's no F's in your answer, you're allowed. If I just ask you to find it, I don't say the word simplify. You don't have to go farther. Okay. Any questions before I move on to the last 2.7.3? Okay. So, the last thing I'm covering in this section is how you find the domain of a composition. So, again, because a composition of functions is still a new function, we can talk about finding the domain of that function. And it turns out there's sort of a special way of finding domains of things which are compositions of functions. There's two things we need to look for when we're looking for restrictions in the domain. The first thing is to look at restrictions in the domain which come from the formula for the composition. So you find a formula for the composition, look at this formula, see if there's any restrictions in the domain. However, there's one other place we need to look for restrictions, and that's we need to look at the restrictions on the domain of the inside function. And the reason we do this is that sometimes when we simplify from here to here, we'll actually be getting rid of restrictions on the domain. And if we do that, if we get rid of restrictions on the domain, we need to still keep in mind that those restrictions are still going to be there. Simplifying might make them not appear to be there, but those restrictions are still going to be there. So we always just look at whatever the inside function is, make sure we have any restrictions that were on that inside function to begin with, and that we haven't forgotten about those when we're simplifying, when we're finding the domain of the composition. So we need to look at the whole formula for the composition. We also need to look at whatever the inside function is and find restrictions from that. And put those two sets of restrictions together to find the domain. Okay. Any questions before we move on to examples? Oh, and sorry, this got kind of cut off. We always want to write the domain in interval notation. Again, usually, well, yeah. Again, I say usually there because if it's just like x is not equal 1, x is not equal 2, x is not equal 3, you can totally just write that as x is not equal 1, 2, 3. But if there's square roots, like if there's restrictions that say like x is bigger than or equal to 2, and another restriction that says x cannot be 3, I do want you to write that in interval notation. Say it's any number between 2 and 3, or any number between 3 and infinity. That sort of thing. So you'll see the answers to these questions, I'll always write them in interval notation. By the way, the other thing I want to mention is these questions I've picked are a little bit on the harder side. There are some that are in there that are easier. I'm doing the harder examples because those are the ones that I know people are going to have difficulty with. So here, the first function, f of x, is square root of 3 minus x. My g of x is square root of x plus 2. So I want to find g circle f of x and its domain. Well, g circle f of x is g of f of x. F of x is square root of 3 minus x. And if I take that and plug it into the formula for g of x, I get square root 3 minus x plus 2. Okay, so now I want to, so there's the formula for the composition. Now I want to find any restrictions. So there's two sources of restrictions. First, we're going to look at the composition, f circle g of x, and look for restrictions from that. So this is the composition. So we look at this thing and we look for restrictions. Well, there's two different square root symbols. Each square root symbol gives you a restriction. So the first one is that. Square root of 3x plus 2. Is it? Oh! Did I do it? No, that's right. That's right. Sorry. Okay. Which we can think of as this. Square root of 3x minus 2 is big. So square root of 3 minus x is bigger than or equal to negative 2. Well, it turns out this thing is always true. Because a square root is always a positive number. Right? Because the thing inside a square root has to be positive. When we take a square root of a positive number, we're still going to have a positive number. So this thing is always bigger than or equal to negative true. So this is always true. Which means it doesn't add any extra restrictions to the domain, which is great. We don't have to worry about any restrictions coming from this thing. The second place we have to look for restrictions is this square root. Right? Every square root you see in the formula gives a restriction on the domain. So the thing inside the big square root has to be bigger than or equal to 0. Also, the thing inside the little square root has to be bigger than or equal to 0. Now this thing, I can add x to both sides, and I get this, that 3 is bigger than or equal to x. Any questions about how I found the domain here using this formula? Oh, sorry. This is supposed to be G circle F, not F circle G. So the other place we look for restrictions is from the inside function. In this case, the inside function is f of x. So f of x is square root 3 minus x. So the restriction is going to be that what's inside the square root has to be bigger than or equal to 0. And if we rearrange this, we get that 3 is bigger than or equal to x. That's the same as the restriction we already found, which is great. We didn't even need to do this step because we already had the restriction down here. In some situations, that won't be the case. We will need to do this step. It'll give you new restrictions that didn't appear down here. Okay, so now there's really only one restriction, right? This doesn't give you any restrictions on x. This is always true. These two things are only true if x is less than or equal to 3. So the domain here is going to be the interval from negative infinity to 3, right? All the numbers between negative infinity and 3 are the numbers which satisfy these restrictions, which are the same restriction twice, really. Is that clear? Any questions about that? Okay. Last example, example 9. So here f of x is x over x minus 2. G of x is 3 over x. Now here, rather than G circle F, we're doing F circle G. So rather than G of F, we're doing F of G, which means we're doing F of 3 over x, which means we're taking 3 over x and we're plugging into that. So we're going to get 3 over x all over 3 over x minus 2. Now one thing to mention here is that the way this is written, it's going to be incredibly difficult to actually work with this and find its domain. So before we go about finding the domain, we're going to want to simplify this. So to simplify this, here I'm subtracting fractions, so I want to put them over a common denominator. So we get 3 over x over, so to put these over a common denominator, I'm going to take this 2, this is basically 2 over 1, I'm going to multiply top and bottom by x to make the bottoms the same. So I'm going to get 3 minus 2x. over x. Right, 2, I'm thinking of as 2x over x. Right, that's what right? I'm thinking 2 is the same thing as 2x over x. 3 over x minus 2x over x is 3 minus 2x over x. So now I've got a fraction divided by another fraction. So I'm going to flip the bottom fraction and multiply. And when I do that, these x's are going to cancel. And I get 3 over 3 minus 2x. So that's the formula for so this is the formula for the composition. This is the formula for f circle g of x, is 3 over 3 minus 2x. Now, if we look at the restrictions on the domain of this, right, all that's basically going to happen is this bottom cannot be 0. 3 minus 2x cannot be 0. 3 cannot be 2x. X cannot be 3 over 2. Right, that's a restriction I get from this. Now, here the inside function is g of x, not f of x, right? The thing inside the brackets is my g of x, which is 3 over x. We also need to look if there are any restrictions coming from that inside function. Well, my g of x here is 3 over x. Since there's an x in the denominator, that x cannot be 0, right? Whatever's on the bottom cannot be 0. So I actually have two separate restrictions. X cannot be 3 over 2, x cannot be 0. And some people ask, why didn't this restriction show up over here? Well, the reason is because we canceled the x's back here. If we hadn't canceled the x's, this restriction would have still been there, because there would have been an x in the denominator as well. So that's the reason we look at the inside function as well, is because sometimes in the process of simplifying this, we've actually sort of gotten rid of one of the restrictions. Okay. So we put those two restrictions together. So x can't be 0, it can't be 3 over 2. So the domain is going to be everything between negative infinity and 0, together with everything between 0 and 3 over 2, together with everything between 3 over 2 and infinity. Right? We've taken out 0, we've taken out 3 over 2, so this is what is left. Again, we usually want to write these in interval notation. Any other questions before I move into the review? Okay. Yes?
Why did you write it in interval notation?
We did. The interval notation was negative infinity to, what was the number? 3. This is also interval notation.
I guess I should have
Okay, there we go. Yeah. No, thank you for asking, because so if I have been known to be inconsistent in the past. I try not to be. And certainly if I ask for this in the test and I want you to write an interval notation, the instructions will say, please write an interval notation. So remember to read the instructions on the test, because I do say things like that if I want you to do it. But, yeah. Okay. Great. So for the rest of the class, I'm going to be doing review, about, again, 25 minutes of it, and then there'll be a little bit of time for group problem at the end. And so I'm going to start off this review by basically just giving you a summary of everything we've covered so far. Again, we've covered a lot of material. It should all, well, 90% of it should have been review from stuff that you either learned in high school or in previous math courses here. So hopefully it's fairly straightforward, but there is a lot of stuff in Chapter 1 and Chapter 2. So I'm going to sort of give you a quick summary of that. So we started off with Section 1.1. Section 1.1 dealt with positive and negative numbers. It dealt with translating words into inequalities. It dealt with absolute value. Those are sort of the main topics in Section 1.1. Again, I covered on the first day of class. There will be one question on the test from Section 1.1. Again, you can check your practice test. There is one question from it. It should be really straightforward, but there will be a question from there. 1.2. 1.2, we dealt with exponents and radicals. So a lot of simplification questions in here. Right? Like things like if we had like x squared, 3x squared over 2yx all to the negative 6. Right? Simplifying something like that is an example of a 1.2 question. Sorry, I'm just going to switch markers because that black is fading. Other things to mention in section 1.2, rationalizing denominators. That's basically the hardest thing in section 1.2. Is how do you rationalize denominators? And the other thing that people sometimes forget is how to deal with things like x to the 3/4, right? That x to the 3/4 I can write as the 4th root of x cubed. So again, those are sort of a couple of things that are in there that are not simplification questions. So like translating this into this, how do you rationalize denominators? Section 1.3, I'll go over here. The title was called Algebraic Expressions. It dealt with polynomials, was basically the first half of that. And factoring polynomials is sort of the hardest thing to do with polynomials. There's also stuff in there about expanding polynomials. That's a lot more straightforward than factoring is, so definitely go over the different factoring techniques. There are a number of factoring techniques which people have forgotten. I know this because people would come to my office hours asking me about them, being like, I don't know how to factor this. I'm like, just use grouping. Grouping is the one that everyone seems to forget. Take the first two terms, take out a common factor. Take the second two terms, take out a common factor. If you have the same thing left, that thing can come out as a common factor. So again, go over those different factoring techniques that I went over. Make sure you can factor all the polynomials in there. If you can't factor polynomials, there'll be a whole bunch of other questions you will not be able to do. There's stuff in here about simplifying rational expressions. Again, rational expressions being fractions with polynomials in them. So, for example, if you're adding or subtracting rational expressions, you need to find the lowest common denominator, right? But we don't use the LCD for multiplication and division. Again, the first quiz, the most common mistake on the first quiz was people trying to find the least common denominator when I had two fractions divided by each other. If you're dividing fractions, just flip the second one, multiply the top, multiply the bottom. Similarly, if you're multiplying fractions, just multiply the top, multiply the bottom. Fractions are these weird things for which multiplication and division is easier than addition and subtraction. There were some questions at the end of this which are called complex algebraic expressions, I think it was called. Basically, go over that. It's basically the most complicated algebra we've seen in the course so far. Make sure you can do all that algebra. Again, I know that's something else people have been having difficulty with. So section 1.4 then was about solving equations. There's a whole bunch of different types of equations I taught you to solve. The simplest are linear ones, like 2x plus 3 equals 6. I also talked about the quadratic formula here, right? How to use that to solve quadratic equations. I talked about factoring. I talked about rational equations. Right? Those are things like 3 over x plus 2 over x minus 1 equals 4 over x plus 1. Right? How you solve something like that. I talked about what are called radical equations. They're not called that in the text, but that is what they are. Things like square root x minus 2 plus x equals 6. Things with square roots in them. This is still going to be 1.4 continued over here. I dealt with equations with fractional exponents. Right? Things like x to the 2/3 equals 1. And, oh yes. And rearranging formulas. Again, section 1.4 was the longest section in chapter 1. Make sure you've got all those different types of equations down. You know how to deal with them, you know how to solve them. And also you know how to tell them apart. So if you see one on the test, you'll be able to figure out which method to apply to it. Because again, one of the common mistakes people make is like seeing an equation that's like this and trying to solve it using the method for quadratics or something like that. That won't work. Okay. 1.5 was on complex numbers. We talked about how to add, subtract, multiply, and divide them. I also talked about things like I to the power of 42, right? How do you do powers of I, and that pattern that comes up. That you know if the power is a multiple of 4, it always gives you 1. If the power is 1 more than the multiple of 4, it gives you I. If it's 2 more than the multiple of 4, it gives you 1. If it's 3 more, it gives you negative I. And also solving equations using complex numbers. So if you have a complex equation with complex numbers in them, or a quadratic equation that you can't use the quadratic formula for because it involves a square root of a negative number, how to use complex numbers to do that. Okay. 1.6. Great, good. 1.6 was on inequalities. How do we solve inequalities? So there were linear inequalities, right? Things like 2 plus x is less than or equal to 3. There were absolute value inequalities. Things like absolute value of x minus 2 is less than or equal to 7. There were polynomial inequalities. And there were rational inequalities. Again, polynomial ones are things that have polynomials in them. Rational ones are things that have fractions with x's in them. The key thing about these two guys is that we have to use these things called sign tables to solve them. Right? We have to basically plug in numbers and see when they're positive or negative. So again, this will be coming up again on sign tables. Actually, they'll be coming up again on Thursday's class because section 3.1 uses sign tables again. And you will see there's a whole bunch of different applications of sign tables that come up later in the course. and that will come up more in calculus. Yeah, and that was sort of section 1.6 here. Okay, 2.1 was basically about graphing points. There was also things like the distance and midpoint formulas. And what else was in graphing points? Oh, and things like finding points with certain properties. Like find all points on the x-axis that are a distance 2 from the certain point. Again, 2.1 was really short. It's another section there will only be one question from on the test. But yeah, we should go over it. 2.2 was basically about graphing equations. The hardest thing in this section was circles. Again, things like just completing the square you can use with circles. There's things like equations of semicircles, graphing semicircles, that sort of thing. So look at the circle questions. There's a whole bunch of circle questions in section 2.2. Again, 2.2 was a short section, only one question. We'll be on the test from there. 2.3 was about lines. So right, you need to know what the slope of a line is, how do you find slope from a graph, how do you graph things using slope. You need to know how to find equations of lines. Again, there were 3 forms of equations that you need to know. You need to know the point-slope form, the slope-intercept form, and the general form. So again, 3 different ways you can write the equation of a line. You need to know about parallel and perpendicular lines, and vertical and horizontal lines. Okay. Section 2.4. This is about functions. So here there was the definition of a function. And this thing that's called the vertical line test to see if a graph is a graph of a function or not. What else is in here? F of x notation. Right? How do you do algebra with the f of x notation? There's, sorry, what was next to here? Domain and range. And there was 2 ways we found domain and range. We found domain and range from a graph. We also found domain and range algebraically. Oh, shoot. I just remembered something I missed. In 2.2, there was also symmetry. Finding if equations are symmetric with respect to the x-axis, the y-axis, the origin, that sort of thing. What else was in 2.4? There were some word problems in, oh boy, problems. There were some word problems in 2.3. There were also word problems in 2.4. So both those sections, you might see word problems from. Again, if you look at the thing that I handed out earlier, it does say there will be one word problem from chapter 2 on the test. There will only be one, but there will be one. So make sure that you go over the word problems. I know people sometimes neglect those. What else was I going to say? Oh yeah. I think that's it for 2.4. So 2.5 was about graphs of functions. There were 3 topics in here. The first was even and odd functions, right? How do you tell if a function's even or odd? There were piecewise functions. And there was transformations, and using transformations to graph functions. Two 2.6 was about quadratic functions. You need to know what the vertex of a parabola is, how you find it, how it's related to the equation of a parabola. You need to know how to complete the square. You need to know how to graph quadratic functions. And also in here was the maximum and minimum word problems. And last 2.7, basically we did, okay, what is f plus g, what is f minus g, what is f times g, what is f divided by g, what is f circle g, right, the composition of those things, and finding the domain of all those guys. So how do you find the domain of each one of those? So that's a quick summary, okay, 20 minute summary of everything that we went over. Anyone have any specific topics they have questions about or want to go over right now? Again, if there's anything that you've seen that was up there and you're like, I have no clue what that is, feel free to ask me about it. Also, let me hand out those Mightiest Point cards. Feel free to write if there's anything in that summary that you want to go over at the beginning of next class. Feel free to write it on a Mightiest Point card. Yes?
On the 2.5, on the even or odd function, what's the thing?
Piecewise functions. Yeah. Yes, Dan.
2.5, I don't remember, I don't think I ever understood what piecewise functions are.
Piecewise functions are functions which
I
have
don't know what they are now.
piecewise functions are more than one functions which have more than one formula. So things that look like this. Right? The idea is you've got f of x equals, you've got this big bracket, and you use this formula. If x is smaller than -1, you use this formula. If x is between -1 and 2, you use this formula. If x is bigger than or equal to 2. So piecewise function is a function which has more than one formula, And each different formula applies for different values of x. Yes? You graph this guy. You take the part of the graph for which this is less than -1. You take this guy, you take the part of the graph here.
The line at x2.
Yeah, you graph. Oh, sorry, let me just, yeah, I'll just quickly show you. I'll do this as an example. So, f of x equals 2. That's the line y equals 2. Which looks like that. Right? We're going to take the part where x is less than -1, which means we're cutting it off here at -1. F of x equals x. That's the line y equals x. We're only taking the part between -1 and 2. So there's an open circle here, solid circle here. Again, open circle because this is, oh, sorry, other way around. Filled in, open. Filled in because it's less than or equal to. Open because it's strictly less than. And then this one is going to look like the graph of x squared. But you're only going to take this part of it. The part that's beyond 2. So piecewise functions have weird graphs like this. Yeah. They come up in situations like in chemistry when something changes from a liquid to a solid. The equation describing it might be completely different. Yeah. Or in engineering when something breaks, the equation describing it will be completely different. So you might have one equation describing like how far a bar is going to bend before the breaking point, and another one which describes how far it's going to bend after the breaking point. Those sorts of things. Yeah. Okay. Anything else folks want me to go over before I throw the group problem up for today? Okay. So I am going to throw the group problem up there. Again, it's the one from last class that I was like, oh, we haven't covered that yet. Uh-oh. Where did it go? I typed it in. Oh, great. Okay, I'm going to pull out, oh, what is it on here? Anyways, I am going